Welcome to our channel. Today, we're diving into the fascinating world of neutron stars. Get ready to have your mind blown by these incredible objects. Imagine a place where a teaspoon of matter weighs billions of tons, where the very fabric of space and time is warped beyond recognition. That's the reality of a neutron star, the collapsed core of a massive star that's gone supernova. These cosmic powerhouses are some of the most extreme and enigmatic objects in the universe, pushing the boundaries of physics as we know it. So buckle up as we explore the mind-boggling world of neutron stars. Neutron stars are so dense they defy our everyday intuition. Let's try to wrap our minds around this. Imagine holding a sugar cube in your hand. Seems pretty light, right? Now, imagine that sugar cube weighing the same as 1 billion tons. That's the equivalent of taking every single human on Earth and squeezing them into that tiny space. That's how incredibly dense neutron stars are. They pack more mass than our sun into a sphere that's only about the size of a city. This mind-boggling density is a result of the extreme gravitational collapse that occurs during a supernova explosion. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The core collapses in on itself, squeezing protons and electrons together so tightly that they combine to form neutrons. These neutrons are then packed together as tightly as the laws of physics allow, creating an object of almost unimaginable density. To give you another analogy, if you could somehow bring a teaspoonful of neutron star material to Earth, it would weigh about the same as Mount Everest. Neutron stars are born from some of the most violent events in the universe: supernova explosions. These spectacular events mark the end of a massive star's life and the birth of something truly extraordinary. It all begins when a star many times more massive than our sun runs out of fuel in its core. For stars like our sun, hydrogen fuses into helium, releasing energy. But for these massive stars, they go through a whole series of fusion reactions, creating heavier and heavier elements. Eventually, they start producing iron in their core. Iron fusion actually consumes energy, so it doesn't help the star hold itself up. The core then collapses under its own immense gravity. This collapse happens incredibly fast, in a fraction of a second. The core implodes, reaching speeds of up to a quarter the speed of light. This generates a shock wave that rips through the star's outer layers, blasting them into space in a brilliant supernova explosion. What's left behind is the incredibly dense, rapidly spinning core, a neutron star. These remnants are like the phoenixes of the cosmos, rising from the ashes of a star's demise. Neutron stars aren't just incredibly dense, they also possess the strongest magnetic fields in the known universe. We're talking trillions of times stronger than Earth's magnetic field, which is responsible for guiding compass needles and creating the auroras. To put this in perspective, if you could somehow bring a refrigerator magnet anywhere near a neutron star, the magnetic force would be strong enough to rip the iron atoms right out of the magnet. These powerful magnetic fields are generated by the rapid rotation of the neutron star and the movement of charged particles within its core. The combination of these factors creates a dynamo effect, amplifying the magnetic field to mind-boggling levels. These intense magnetic fields play a crucial role in many of the observed properties of neutron stars, including the emission of powerful beams of radiation that make some neutron stars appear to pulsate, hence their name, pulsars. Hold on tight, because neutron stars are also the universe's ultimate spinners. Imagine an object more massive than the sun spinning multiple times per second. That's the reality of some neutron stars known as pulsars. These cosmic whirlwinds get their incredible spin from their parent stars. Just like a figure skater pulling their arms in to spin faster, as a star's core collapses into a neutron star, its rotation rate increases dramatically due to the conservation of angular momentum. Some pulsars spin hundreds of times per second, and the fastest known pulsar whips around a staggering 716 times per second. That's faster than the blades of a kitchen blender. This rapid rotation is so precise that pulsars are often compared to cosmic lighthouses. As they spin, their beams of radiation sweep across space, and if Earth happens to be in the path of these beams, we detect them as regular pulses of radio waves. Neutron stars can be solitary wanderers in the vastness of space, but sometimes they find themselves locked in a gravitational dance with another star. These systems, known as binary systems, offer fascinating insights into the lives of these extreme objects. Imagine two incredibly dense objects, a neutron star and another star, possibly even another neutron star, orbiting each other in a cosmic waltz. Their immense gravity creates powerful tidal forces that can distort their shapes and even rip material from their companions. These binary systems are like cosmic laboratories, allowing astronomers to study the properties of neutron stars and the effects of strong gravity in ways that wouldn't be possible with isolated neutron stars. One of the most exciting aspects of binary neutron star systems is that they can eventually merge in a spectacular collision, creating ripples in space-time known as gravitational waves. Neutron stars are like the lighthouses of the cosmos, beaming out powerful signals that can be detected across vast distances. These signals aren't light in the way we typically think of it, but rather radio waves, X-rays, and gamma rays. Remember those rapidly spinning pulsars we talked about? Well, as they spin, their powerful magnetic fields channel charged particles along their magnetic poles. These particles are accelerated to incredibly high speeds, emitting beams of radiation that sweep across space like a lighthouse beam. If Earth happens to be in the path of one of these beams, we detect a pulse of radiation every time the neutron star rotates. These pulses are incredibly regular, like the ticking of a cosmic clock. By studying these pulses, astronomers can learn a great deal about the properties of neutron stars, including their rotation rates, magnetic field strengths, and even their internal structure. Neutron stars are known for their incredibly precise rotation, but even these cosmic timekeepers can have their moments of irregularity. These sudden changes in a neutron star's rotation rate are known as glitches. Imagine a spinning figure skater suddenly changing their speed. That's kind of what happens during a neutron star glitch, but on a much grander scale. These glitches are thought to be caused by sudden shifts in the neutron star's crust, or changes in the flow of superfluid matter within its core. While glitches are relatively rare events, they offer valuable insights into the internal structure and dynamics of neutron stars. By studying how a neutron star's rotation changes during and after a glitch, astronomers can learn about the properties of matter under these extreme conditions. Beneath the incredibly thin atmosphere of a neutron star lies a surface unlike anything found on Earth. Imagine a solid crust, perhaps a few kilometers thick, made up of mostly iron nuclei packed together in a lattice structure. This crust is incredibly strong, able to withstand the immense gravitational forces present on a neutron star. But what lies beneath this crust is even more mind-boggling. As we delve deeper into the neutron star, the pressure and density increase dramatically. The neutrons themselves begin to behave like a superfluid, a bizarre state of matter where there is zero viscosity, meaning it can flow without any resistance. This superfluid core is thought to play a crucial role in the glitches and other unusual behavior observed in neutron stars. When two neutron stars in a binary system finally spiral in towards each other, the result is a cataclysmic explosion unlike anything else in the universe. This cosmic collision releases more energy in a fraction of a second than our sun will emit in its entire lifetime. As these incredibly dense objects merge, they create ripples in the very fabric of space-time known as gravitational waves. These waves travel outward at the speed of light, carrying with them information about the extreme events that created them. But that's not all. Neutron star mergers are also responsible for creating some of the heaviest elements in the universe, including gold, platinum, and uranium. These elements are forged in the intense heat and pressure of the collision and are then blasted out into space, seeding the surrounding interstellar medium. Neutron stars might seem like exotic and distant objects, but their study has profound implications for our understanding of the universe as a whole. These extreme environments serve as cosmic laboratories, allowing us to probe the fundamental laws of physics. By studying neutron stars, we can learn about the behavior of matter under extreme densities and pressures, conditions that we can't replicate here on Earth. This knowledge can help us understand the early universe, the interiors of black holes, and the ultimate fate of massive stars. Neutron stars also provide a unique testing ground for Einstein's theory of general relativity. The strong gravitational fields around these objects can distort space-time in measurable ways, allowing us to test the limits of our understanding of gravity. So the next time you look up at the night sky, remember those tiny, distant neutron stars. They are not just fascinating objects in their own right, but also powerful tools for unlocking the secrets of the cosmos. Thanks for watching. If you enjoyed learning about neutron stars, don't forget to like, subscribe, and hit the bell icon for more amazing space facts. We've only just scratched the surface of these incredible objects. There's still so much more to discover about neutron stars, from their bizarre interiors to their role in creating the elements that make up our universe. See you next time for another cosmic adventure.